A chemist might spend 50 or even 75 or even more % of his time simply purifying substances. In an earlier screencast, we looked at some basic separations, like, say, oil from water. But life isn't really that simple, isn't it? Imagine a chunk of dirt. It must have perhaps hundreds or even thousands of different unique substances within it. I mean, look at that. There's a leaf in there. God knows how many different molecules, different substances are in there. In this screencast, we'll look at how we can purify any mixture, regardless of its complexity or of its phase. And we'll think about what methods are suitable for each type of mixture. This is Screencast 3.9. Okay, here's some methods we saw before. Let's take a look at them again. For separating a immiscible liquid mixture, a good method is layer separation, for example, using this separatory funnel. So you use it for two liquids that are insoluble in each other. Hopefully they haven't formed a milkshake, right, an emulsion, and you can just separate them right at the line there. Suppose you've got an insoluble solid in a liquid. That should be an easy separation. We could just filter it out. So filtration, this is gravity filtration here, which, by the way, is a slow method, is a nice way to purify insoluble solids from that sort of a mixture. If you have a solid that's dissolved in a liquid and you want that solid, you can try to crystallize it. This is a fantastic method for dissolved solids, and it's a bit of an art form. It requires a bit of work, and it can be problematic, but if it works well, boy, you get wonderful mixtures. It probably won't work well if you have a whole bunch of different solids dissolved in that mixture, which out in Mother Nature is oftentimes the case. Say you got a liquid-liquid mixture, like oils or gasoline. These are volatile, and you should be able to simply heat them up and separate them based on their boiling point by distillation. So it's a good method for volatile liquids. Suppose that when you apply heat, it just turns into black tar, which all too often happens. Or suppose those boiling points are like 300 or 400 or even higher degrees Celsius, and you can't seem to get the thing hot enough. Well, a nice trick is to use something called vacuum distillation, where one of these devices, I think it's that one right there, will be applied to a vacuum. This reduces the boiling point and can make things much milder. So use it for either sensitive liquids or high boiling mixtures. If they differ in boiling point by only a degree or two, or even less, you just don't have enough surface area for the boiling condensation process to repeat itself often enough. And a cute device, an expensive device for doing that, is to create more effective surface area by using a spinning band. It typically looks like a spinning window screen, so that makes it far more efficient. And so spinning band distillation is the method of choice if you have very close boiling liquids. Let's imagine you have a mixture of a solid, many solids dissolved in a liquid. You can't really crystallize it because they're going to crystallize out as mixtures. It won't really work. They'll probably be amorphous. And so a method for this can be to use chromatography. Now this is paper chromatography here, and almost nobody uses that on an industrial or a preparative scale. It's fun, and it demonstrates the technique, but it's rarely very useful. Usually they're going to use a different solid support. Typically they'll use silica gel, which is purified glass on a solid backing, and you elute some solvent, and they separate based on their adhesion to that solid phase. So this is known as thin layer chromatography, and that's a great method for separating out small amounts of solids. You can literally take a mixture and scrape off each solid mixture. As things scale up, they might become preparative TLC for a larger, thicker plate, or they might become liquid chromatography for a three-dimensional column of silica gel or some other solid support. And this method gets used over and over for soluble solids that are in a liquid mixture. And it works for complex mixtures as well. If they get really complex, you might want to go with, oh, I'm sorry, this is actually for gases. If you want to separate gases, you can use the same technique of adhesion to some solid layer, but you got to be able to trap everything in the gaseous phase, and this is known as gas chromatography. Here's the one I wanted to refer to before. This is for separation of complex mixtures. They can be liquids or they can be solids. You have a column, the stuff is pushed through it, the mixture is pushed through it. It will adhere to different amounts to that solid support. As each one elutes, there is some kind of identification method that leads to a peak for each pure substance. Note that they might overlap a little and require further purification. But this can be a great method. As it comes out, it typically drips out of the back of this thing, you can collect it in a vial. And this is known as HPLC, or High Performance Liquid Chromatography. Of all the methods, it's probably the most generally useful here. These are a bunch of different purification methods. Note that none of these methods identifies what the heck it is. You might get a peak, but it doesn't tell you what it is. In our next screencast, we'll look at identification methods. This is Screencast 3.9.